Hello everyone, and welcome to the channel. So I know this video has been a long time coming. I was on a summer break, did some traveling, dealt with a bout of COVID, but yeah, now I'm back in getting into the rhythm of producing videos again. So expect the channel to ramp up in the coming weeks. So in this video, we'll be starting the work on a CPU Breakout board PCB. I really want to clean up the wiring mess on my breadboards, and so this is kind of taking priority over the feature work I had initially planned. Today I will be working through a number of small cleanup tasks I have accumulated over time in order to prepare the circuit for designing the PCB. I hope you enjoy. So there's been a lot of new faces on the channel since I last went over my goals for this project. So let's do a quick recap. I want to build a 65C816 computer on breadboards, which runs at 4 MHz. So a reasonable speed, not too fast, but not too slow. I want to use through-hole ICs only and no programmable logic. So this is going to be a discrete build. It will have 32K of RAM, 32K of ROM, and 512K of extended RAM to make use of the expanded addressing capabilities of the CPU. In terms of I/O, we'll have a 65C22 and a 65C21, the latter of which I'm adding because it's a less common chip. It will be nice to learn how to work with it and how it is different than the 65C22. And finally, we'll have a 65C51 for the UART, I guess to complete the Western Design Center collection. I know this one has a hardware bug, but it will be nice to show it on video and show how to work around it. And I'll switch to a different UART in the next revision. All right, so this is our computer where we left off the last time. As you can see, it's still running the Hello World program. And in this video, I was initially planning to add more features to the computer. But after taking some time to think about it, I really want to clean up the mess that is these wires. Especially for the videos, because you guys probably can't see what's happening in the boards when I work on them. And so I want to clean up this. Let me put up a schematic and talk you through what my plans are. So this is how I see the structure of the project. So you can subdivide the breadboards into a few distinct areas. The first one and the most important one is the CPU and glue logic. This is where you have the CPU, the bus management, and all the signal generation, as well as the reset signal and potentially even the CPU clock, which we'll talk about later. The second area is everything that's related to debugging. So that's the main clock with the manual and slow modes, the LEDs for the status of the computer and the bus, and the Teensy monitor as well. All of these modules are kind of related to what you do when you're actively working on the CPU, so either writing new code or troubleshooting a problem, but they're not strictly necessary in order to run the CPU, let's say, in quote-unquote production. So you could completely remove this and the CPU could still work, assuming you had a clock. The third area is memory and I/O control. So these two modules hold the memory map of the CPU. They generate the chip select signals for peripherals. So it makes sense to group it with the memory and the ROM because they'll need the same signals. I can see here also something to sum the RQ signals from peripherals and handling wait states and DMA accesses on this board. And then finally, you have the peripherals, of which we currently have only one, which is the LCD screen. But this is going to grow in the future as I add more components to the CPU. So for now, this is kind of going to stay in a breadboard, and we'll probably build multiple PCBs out of multiple peripherals. So with this, you can see my plan for building PCBs. Each module is kind of going to go into its own PCB. And I will start by the CPU and glue logic, which seems kind of the main one. So now we have to talk about the form factor. So as you know, I've mentioned already a couple times in this channel that I was looking at a backplane system. Initially, this seemed like a good idea. I've been following Troy's HBC56 with interest, as I really like the form factor and hackability of the project. I also really like the Zolatron 64, which I find really sexy with its aluminum structure and your card sockets. But unfortunately, when I would love to build something like that for myself, it kind of doesn't look good on video. And so that's actually kind of my constraint. I want something that looks good for you guys so that you're able to see what the CPU is doing. And so I've been thinking about doing more kind of a flat build, something like BB816 Computer. It renders really well on video. Or if you look at a PCB versions of this, James Sharman Pipeline CPU is a good example of something that has a lot of functionality, but also looks great on video. And so this is kind of the things I want to model. And so this is what I think I'm going to do. I'm going to do PCBs that are mounted horizontally for top-down shots on the video. And for the backplane, I'm going to continue using breadboards. So I know there's a few of you that are following along and trying to build this computer yourself. And so I want you to be able to keep hacking on it easily. And so using breadboards to join multiple PCBs is going to allow that. So if you look at my 6502 project, this is kind of how it's going to look. There's going to be a header connector at the bottom that you're going to be able to plug on a breadboard and get your signals from there. So as I said, the first board I'm going to start with is the CPU board. So let's look at some goals I've set to myself for the CPU board. So I want the CPU Breakout board to be self-contained so that it can be used on its own to drive other projects. I wanted to expose all the CPU features, even arcane ones that you may not want to use in most projects, but I wanted to be feature complete. I need the ability to rebuild parts of the design on a breadboard. So as I'm iterating on the CPU and glue logic, if I want to replace some parts of the circuit with a CPLD, for example, I need all the internal signals exposed so that I can reuse them. And I also want to pay attention to signal integrity. Of course, it's going to be limited by the breadboard interface, but this is going to be a 4-layer PCB with 2 ground planes, and it will have good ground return path, at least internally. And I want to avoid sending signals with fast edges out. So anything coming from a 74AC chip, for example, or if I do, I need to consider terminating them. So this is our schematic where we left off the last time. In order to work on the schematic for the breakout board, I'm going to create a new sheet. That will be the CPU breakout. So let me move the CPU as well as the power circuit, the reset circuit, and the glue logic to the breakout board. So I'm going to cut this. And I'm going to do paste special here because I need to keep the existing references, otherwise they're going to be cleared. Now I said I wanted this board to be pretty self-contained and able to be used independently to drive other projects. And so I don't really want to include this whole clock circuit because it's quite complicated and you don't really need it to just basically run the CPU. I see this more as a debug clock that you would use additionally when debugging a specific problem that you have with the hardware. And so in these specific projects, I'm going to put the debug clock on a separate PCB. But I still want to have a clock here in order for the CPU to run. And so I will just add an oscillator circuit. And I'll do that next to the reset circuits. And I'll rename this clock and reset. And I will also rename the file. So let's get started on that. So firstly, let me get a bit more space. I'll move this back to an A4 sheet. Awesome. So what I'll do is I'll go in our debug clock. And by the way, I'm also going to rename this. And I'll take the oscillator and 1 flip-flop. So this one is going to be 8 megahertz. We are not going to use the enable pin, but it needs power and ground. The flip-flop has 1 second unit and a power supply. We're not going to use the second flip-flop, but we need to pull up all the inputs. And we also need the chip to be powered. They also need 2 decoupling capacitors. And the flip-flop is going to divide the frequency by 2 and ensure that we have a perfect 50-50 duty cycle. So one thing we also need for this clock is the ability to disable it when we want to use the debug clock or the clock for the monitor. So we need a tri-state output here. And thankfully in the glue logic, we have 1 buffer left. So I'm going to take this one and use it here. So this is going to be controlled by the clock enable signal. And at the output, we'll have our clock in signal. And actually clock enable is active low. There we go. Now let's have a look at the reset circuit. The first thing I'm seeing is that we have a chip here to get us 3 flip-flops, but the 74HC175 is kind of a rare chip. I guess most people don't have it in stock, and so I think we can replace it by a 74HC74, given that we have one here and a second HC74 would give us the 2 flip-flops that we need. So let's do that now. So it also has a power supply. So we can take this one and put it in a chain. And then at the output, we'll have our inverted reset and active high reset. We are not using the intermediary inverted outputs. And then the clock is always the clock. And the reset is the output of the Max 705. There we go. And the set we can connect to VCC because we're not using it. Okay, so this should be everything. We can replace this one. And there we go. This is our new reset circuit. Now, the next thing I want to look at is the Max 705, because at the moment we are not using the profile monitoring and the watchdog input. And if you look at Mother, it's also a pretty expensive chip at almost €7. And there's not a lot of stock available at the moment, but there is another chip that we can use. That is the DS1813-5, which is even smaller. It uses a TO92 package, and it's much cheaper at almost €3, so that's more than half. And it has the same functionality. It will monitor the incoming power on its second pin, and it will provide an active low reset when the power goes under a threshold or when first powering up the circuit. It also supports a push button for a push button reset. So basically it has all the same functionality except the power fail monitoring and the watchdog in the Max 705 that we were not using, and it's much cheaper. So I'm going to replace our Max 705 by this chip. And if we look at a typical application, this is how it works. So you will connect the reset pin of the DS1813 to the push button and to the microprocessor reset. So it's a very simple application. And if you look at the electrical characteristics, the trip points of the DS1813-5, so that means a 5% tolerance on VCC, is at max 4.75 volts, which is identical to the Max 705. So it will trigger at the same place in the voltage. And the reset will last typically for 150 milliseconds, which is fine for our application. So let's do that. So KiCad doesn't have a symbol for it, but I made one and included it in the project library. So this is it. So I will be removing the Max 705 and using this as the reset. So of course it needs power. There we go. And then our push button circuit, we can just connect to its reset pin here. And so in order to programmatically generate a reset, the manual reset input will be here. However, there is one additional consideration that we have to keep in mind, and that is if you look at the block diagram of the DS1813, how the reset output works, you can see that there is a 5K pull-up and a transistor that can pull it to ground when the delay is active. So that means that the reset output is open collector, and that means that when it's active, it's wired directly to ground. So that means that we cannot connect a normal logic gate here to the MR pin. We either have to use a diode or another open collector gate. So we have to keep this in mind. I will add this to the schematic. Okay, I'm also going to remove the 10 microfarad capacitor that we have here because we are only going to have a single one on the board, and that's going to be part of the power circuitry. So let's count our decoupling capacitors. We don't need one on the DS1813. We need one on each flip-flop and one on the crystal. So that's 3 coupling capacitors, so we have one too much here. And this is all our components. So let me add all the inputs and outputs. Now on this circuitry, we are currently using the main clock. Of course, the main clock is equal to clock in delayed by 20 nanoseconds. And I think in this application, it's fine to use clock in directly because we only want to count the number of clock pulses between the reset activating and the reset clearing. And this way we don't have to send the normal clock into this module. Okay, so let's input the pins at the breakout level. Oh, and one thing we should say is that MR is active low. All right, so this is our clock and reset updated. Let's implement it on the breadboard. All right, so let me zoom in on the clock and reset so that you guys can see what I'm doing. Let me start by putting up the old circuit, so the MAX 705 and the 74HC175. So let me start by plugging in the DS1813. There we go. So it needs power on pin 2, which is the middle pin, and ground on pin 3, which is the right pin. And then our reset switch can be connected to pin 1. There we go. Now we need the 2 flip-flops. So these also need power and ground. And decoupling capacitors. So we have the clock in signal coming through this green wire here to the connector. So we can connect it to pin 3 and 11 of the flip-flops. Now the reset signal from the DS1813 goes to pin 12 of the flip-flop here. And then it goes to all the reset pins, which are pin 13 and pin 1. Then pin 9 goes to pin 2, and pin 5 goes to pin 2. Then we have to connect pin 4 and 10 to VCC. And then finally, the output reset signal goes to the gray wire in this connector, and then goes here to the monitor and to the CPU via the yellow wire. And this goes to pin 5 of the third flip-flop in the chain. Okay, so let's try it out. And I'm seeing a lot of current being drawn, so that's a problem. Also, the LCD wasn't displaying hello world. Okay, so I see my problem. I have reversed the orientation of the DS1813. The pinout I was looking was actually a bottom view. So let's reverse it. Yep, that is the correct orientation now. Let's turn on the power. And there's still an issue. Okay, so the issue was this little white wire here was touching one of the pins here and was making a short. Let's turn on the power again. And it works. Awesome. Can I reset it? Yep. So you can't see it because this is on the fast clock. So let's change the clock and reset. Actually, let's go a bit faster. Yeah, you can see it working here. Awesome. Now let's add the new oscillator. So here's my 8 MHz crystal. It needs power and ground and a decoupling capacitor. Then the output is on the top right pin and it goes to pin 11 of the top flip-flop here. Then we need to connect pin 8 to pin 12 and pin 10 and 13 to VCC. Now, the only issue with this is I need to send the output of the flip-flop all the way to the buffer that is over here that I've reused in order to reduce the chip count on my PCB. But of course, this is not really ideal on the breadboard. So I've made a little jumper wire, which has 4 pins. One is to send the output of the flip-flop. One is to receive the final clock. And one is the enable signal. And then we have a ground because I want to make sure that I'm sending the ground with the signals. So let's connect it. So we need to disconnect pin 10 and 9 from VCC because previously we weren't using this buffer. And I'm gonna add a ground wire here to send the ground with the jumper. So as you can see, the white wire is going to be the ground, the purple wire is going to be the output, the blue wire is going to be the input, and the green wire is going to be the enable. So let's wire this up on the other side. We need the ground on the white wire. We need the output of the flip-flop, which is pin 9, to go to the blue wire. The purple wire is the output, so we can connect this to the same point as the other clock is connecting here to go to the CPU board. There we go. And the green wire is the enable. And so we have to be able to control the enable between this new clock and the debug clock, which is here. And there's also the question of the monitor, and I kind of forgot about that. So I'll talk about it later in the video. For now, I'll just disconnect it. And what I'll do is I will pull up both of the enabled signals, and I'll add a jumper that I can switch between them to select them. So I need to change this to a pull-up, and I can add one here as well. There we go. And then I can take a wire to ground, and then I can connect either here or here. All right, so let's try it out. So let's try it with the new clock enabled. And looks like it's working. And now I'm going to switch to the debug clock, and we should be able to see the slow clock pulsing. And so now if I reset and I make it go a bit faster, you can see it working here. Awesome. So it looks like it works. Let's go back to the schematic and see what other cleanup we can do. Okay, so now let's look at the power section. Okay, so Adrian from the future here. I'm going to skip this section because it was really long and not really interesting. I'm basically just adding a DC jack as the power input and a fuse between the DC jack and the power. I don't think the fuse is actually necessary for our purposes, so I'll be removing it later, but I'll keep the barrel jack for a good power connection. Okay, so the next thing I want to look at is our connector. So as you can see on my 6502 project, I'm going to do a connector at the bottom. And if I want this to plug into a breadboard, a reasonable size is 50 pins. And I'm going to have to split it in a 40-pin version and a 10-pin version so that people who want to solder pin sockets to this header will be able to do so because you cannot find 50-pin sockets. So let's add this to KiCad. There we go, and we'll see if we need any more than that. And I already know that there are some signals that I don't want to place on this header because I'm probably going to need to use all of them, and any signal that are seldom used or are used only for debugging, I want to place on a secondary pin socket. So I'll add another 10-pin connector and we'll see again if this is the right size. On the main breadboard connector, I want the 5 volts output, the ground, we need the reset signal, we need the manual reset signal, and as you can see, I've updated off camera the manual reset signal because it's an open collector signal, which is signified by this symbol so that we know that it is open collector. I've also updated it here. Then I'm going to add signals related to the clock input, the clock enable, the output clock, and the inverted input clock. Then we'll have interrupt signals. I'm going to add the address and the data bus. And since on the breadboard the connector is going to be rotated 90 degrees to the left, we actually have to reverse this. There we go, so that the most significant bit is on the left. Okay, so on the remaining connectors, we can already see that we're going to need more space, but we'll have ready in, bus enable then ready in, and wait, VA, and sync. We want read write, read, then we want write. So the CPU ready pin I'll put on the auxiliary header. We do need the emulation pin, the MX pin. And actually I want to decode this pin into M and X, so I'm just gonna add it twice here temporarily. We need to clear one pin here to add write, and I think that's gonna be the abort pin. There we go. We need to add our positive reset, and this can go also to the auxiliary connector. Now let's have a look at our sheets and see if there's any other signal that we want to bring out. So on the clock side, I don't think there is anything that we need. Actually, it might be useful to bring out the 8 MHz signal here, just in case it becomes useful in the future. But I don't see anything else. And we'll put this on the auxiliary connector. Now let's look at the glue logic. Do we have anything that we want to bring out? Okay, so we definitely want all our clock phases, including all the out of phase ones. We can bring out the registered ready, as well as the output enable of the buffer, the inverted bus enable, and I guess I'm going to add a connector just for this. I'm also going to add grounds. And over here we want VDA, VPA, and then VP and ML. Okay, so I need to add a ground here as well, and that makes it a 12-pin connector. And of course, the ground return path for the signals are not going to be great because the ground is going to be at the left of the connector. And so really what you would want to do is add grounds in every other pin. But that would limit the number of signals that we can plug into our breadboard. And also the ground return path on a breadboard are going to be pretty bad anyway. You're going to have pretty big loop areas to go from one of those pins to the power rails on the breadboards anyway. So I think that's fine for our purposes here. So the next thing I want to do is someone told me that I should update my pull-ups to be 3.3K, and that would give me better noise resistance. We also have to add back the pull-up on the RQ line because we are not driving this line anymore here in the breakout board. If we don't connect the RQ line, it's not driven. So I'm going to do that now. And also any pull up or pull down that I only use when either the clock is stopped or running very slowly, or with the bus enable tied low. So the CPU output buffer is disabled and nothing else driving the bus. These are pretty rare cases. We don't really need strong pull-ups for this. And so we can update those values to be 100K, and that will reduce the power consumption. So let's update our pull-up values. Again, here, these are only necessary if bus enable is tied low, but nothing else is driving those signals. So we can make all of these 100K. It's going to be a pretty weak pull-up, but it's just to provide a defined value when the bus is not driven. Here on ready in, we need 3.3K because this is going to be an input signal. And on the ready pin, I'm going to leave it at 1K because we measured the propagation delay of changes to ready based on the time constant of this circuit. These need to be 3.3K as well. Now read-write is tri-stated by bus enable. So this is another of those 100K cases, and bus enable is an input signal. I guess we should probably add one here because this pin can be tri-stated. So I'm going to make this a pull down so that the default state is the clock is low. All right, I think that's everything. Okay, so I'm not going to update all my resistors on the breadboard project. I don't think that's useful and something that you would want to watch, so I'll go directly to the next item. So the next thing I want to do is look at the glue logic. There are some improvements I want to make there. The first one being I want to include in the CPU breakout board the bank 0 signal, because I think that's a really useful signal to have if you want to build a simple address decoding using this breakout board. So let me go into the address decoding and copy this. Let me see if I can get a bit of space. Starting to get a bit cramped. Maybe I'll increase the size of these sheets at some point, but we can build the bank 0 circuit here. We just need to plug in all of the address lines, and out we get the active flow bank 0 signal. And I'll add this as an output of this sheet. So now we can import it here. And we need to free a pin here. And that's going to be the inverted clock. So we have to replace this. Now, does this order make sense? No, really. There we go. Oh, and we need the power supply for this gate. And an additional decoupling capacitor. And I'll remove this 10U here because we already have it at the top level. So I will update the address decoding sheet to not have this here anymore. And I need to add bank 0 as an output. No, apologies, it's an input. Okay, so this video was getting a bit long, so I decided to cut it in half. I still have a bunch of modifications I want to make, such as removing some of the AC chips that are in my build and that are driving signals to the breadboard, and figuring out what to do with the monitor clock now that we have 2 clock enable inputs here. You know, how I'm going to chain my 3 clocks so that they don't step on each other. And there's probably other things that I'll find, but we're getting closer to starting work on the actual PCB. I expect that's going to be either in the next episode or the following one. One thing is for sure is I want to get this PCB designed and sent to the fab so that I can focus on adding features to the computer again. So anyway, I'll release the second part of this video next week. So I hope to see you then. As always, if you have any questions or feedback, let me know in the comments, and I hope to see you in the next video. Goodbye.